Lesson 44 is a fairly intense one. We'll probably do it in two parts. It starts off with acceleration of a mass on a spring. So we're basically going to be dealing with horizontal springs here, which means that gravity is not generally going to affect the oscillation of the spring. And it says as a mass bounces back and forth in a spring, it will have a changing acceleration, which we've already discussed. So let's just quickly review that. If I have a spring and then I stretch it out, it's going to go back and forth with its equilibrium position in the middle. It's going to have a maximum velocity in the middle and an acceleration of 0 in the middle of its oscillation, or at the equilibrium point. On either ends, when it's stretched the maximum or compressed the maximum, it's going to have a velocity of 0, and the acceleration is going to be the maximum. So even though you say for an instant, it's not even moving, but it's defined as the acceleration is the maximum, because it's accelerating here, and then its acceleration is becoming less, and it has an acceleration of 0, and then it starts slowing down, right? So for it to have a positive acceleration and then a negative acceleration, it must reach 0 somewhere between those 2 points. Here's the formula that we're going to use for the acceleration of a mass on a spring. It's just a derived formula. The net force simply equals, since gravity is not an issue here, or not a concern, then the net force is simply the restoring force, and therefore ma equals negative kx, and that formula can be manipulated to give you this. The acceleration, to calculate the acceleration of a mass on a spring, is negative k times the displacement, the amount of the distance that a spring is compressed or expanded, and divided by the mass. So example one's pretty straightforward. We're just plugging numbers into that formula there with that k value there. The only difference is in A it says it's stretched, so we're going to use a positive value for x, and in B it says it's compressed, so we're going to use a negative value for x. And I'll reiterate this: the negatives just really indicate direction. They're not really that important in this unit. So here we go. A is very simply A equals negative kx over m. And there it is. Don't forget to convert your centimeters to meters. Plug those numbers in, and you get negative 26 meters per second squared. Okay, and for B, it's exactly the same thing. So for now, we're going to use 0.25 for the displacement, and we're going to make it negative. So you get a positive answer. So one will be positive, one will be negative, because they're obviously accelerating in opposite directions. All right, and that was easy because the 0.25 just cancel each other out. Oops, and there should be a negative there because I should have put a negative here. So it's actually a positive answer. Moving on, now we're going to try and calculate the velocity of a mass on a spring. And the first part of your notes here just reviews what we talked about. The only part that we haven't talked about here, well, actually, let's go through the whole thing. So remember the examples above. The mass is just being released from rest, so its velocity starts at 0. It accelerates back to its equilibrium point, at which point it has a maximum velocity. The elastic potential energy that was stored in the spring is converted to kinetic energy as the mass goes faster and faster. So in addition to this formula that you already know, we're recalling another formula from the previous units, from the energy unit, and that is the formula for elastic potential. And you will recall that that is the formula for elastic potential energy. Continuing, at the equilibrium position point, there is no elastic potential energy remaining, so it's all become kinetic energy. So this is like the pendulum. And when you pull the pendulum back, at this point, it's all EP, and then all of that gravitational potential energy gets converted to EK. Same thing with the springs. In the middle, when it's at its equilibrium position, all the elastic potential energy has been converted to kinetic energy. And then the spring continues to compress or expand, and then all that kinetic energy gets converted back into elastic potential energy. Here's another important thing. We call the furthest that the mass is from the equilibrium point, the amplitude, capital A, of the spring. It's measured in meters. If we want to calculate the maximum velocity of the spring as it passes through the equilibrium position, we can use the conservation of energy. So we've got EM equals EM prime, the mechanical energy before equals the mechanical energy after. And as we said, we're talking about elastic potential energy and kinetic energy. Okay, and we know that when we stretch the spring, and when you're just kind of holding the spring, it's all elastic potential energy and no kinetic energy. So therefore, that one's going to be 0. And then the mechanical energy afterwards, in other words, what's the mechanical energy when it's at its equilibrium point? At that point, for an instant in time, it has no elastic potential energy and is all kinetic energy. So this is very similar. You've seen this process before. We're just doing it in a different context now. And then that should look vaguely familiar. So now 1/2 kx squared is going to equal 1/2 mv squared, and we're trying to solve for velocity. So you'll notice that the halves cancel out. And I'm just going to do it over here. And therefore, the velocity squared equals kx squared over m. Kx squared over m, and therefore the velocity equals the square root of kx squared over m. Now the x in this is a very specific x, and we're going to call it the amplitude. So instead of x, you could just leave it at x, it doesn't really matter, but because it's a specific one, because it's specifically the maximum amount of stretch that you can get in the spring, we're going to call it A. And so we're going to rewrite this as A squared. And you can just leave it like that, or if you want, you can, oopsie. You can take the square root of A squared, pull it outside, and that is it. That is a new derived formula for calculating the velocity, the maximum velocity at the equilibrium position of a spring. Okay, example number 2. A 17-kilogram mass is pulled 13 centimeters away from its equilibrium point on a spring with a 367 Newton per meter constant. Determine its maximum velocity as it goes through the equilibrium point. Formula's right there. I'm not even going to write out all the variables. Maximum velocity equals the amplitude, 0.13, 13 centimeters, so 0.13 meters, times the square root of the spring constant, divided by the mass, and that's going to give you an answer of 0.6 meters per second. Okay. Shall we do this next part? Yes, let's do this next part because the next part it still refers to masses on springs, and now we're going to do a little manipulation to calculate the period of a mass on a spring. So it's possible to show that simple harmonic motion very closely resembles circular motion, and you should go onto YouTube and so you can see this because it's really cool. I know I say everything in physics is cool, but that's only because it's true. Yeah. Tom Altman and SMH at the Exploratorium. Watch this video. I can't show it to you right now on this because it takes up so much, huge amount of memory. So go to YouTube, watch that video, and you'll clearly see how simple harmonic motion, like a spring oscillating back and forth, mimics circular motion in a really profound way. It's really cool. And if that's the case, if that is the case, then we're going to use this formula here from our previous unit. That's the formula for velocity, something going in a circular path, the velocity of something going in a circular path. And in this case, we're going to change the r, the radius, to a, because if something is going, here's a circle, and here's a simple harmonic oscillator, and the oscillator is just going d, 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 d. And if you had an object going around the circle, and if you watch the video, then you'll know exactly what I'm talking about. If you watch the video, if this is going around in a circle, like this, and then you have, including green, that, and this, that, and they will exactly match up, If you're looking at this from this angle here, this dot and this dot, as this goes back and forth, and as this goes in a circle, they will exactly match up, and therefore the amplitude, this is the amplitude in the simple harmonic motion, equals the radius of the circle. So that's why we can make this r into an a. Okay, and then we are going to use this formula and the one that we just did in the previous section, which was a equals the square root of k over m, and now we're going to set that equal to, and we're going to solve that formula for period, in other words, t, and that's going to give us a new formula for the period of a mass on a spring. So if you're solving for period here, there are multiple ways you can do this. Probably the easiest way to do it is to, well, first of all, you can see that something cancels out. The A's both cancel out, so the amplitude is irrelevant. And then we're going to just move the T up here. And then the simplest mathematical way to get rid of that Km is just multiply both sides by the reciprocal of the square root of k over m, which is the square root of m over k. And as you can see, if I do this, I'll get the square root of mk divided by the square root of km, and those will become the square root of 1, which is 1. So you can see how that cancels that out. And here's our new formula. That is for calculating the period of a mass on a spring. And that one is on your formula sheet, so you don't have to know how to derive it, but we just did it. And then the question example number 3 says, using the information from the previous example, determine the mass or the period of the mass. 2 pi, the mass was, what was it, 17. The spring constant was 367. 1.4 seconds is the answer to that question. So that is to calculate the period of a mass on a spring. All right, we'll stop this video here and then you can go on to the next one, which will be for pendulums.